Alright, so the big thing about units. So I'll wait on that at the moment, just to get this out. Like units, it's units, and then it's significant figures for the first two units. Yeah, I'll look at get the book here. See the first unit is units and measurement. So that's why this is real important. So first, you already read the introduction?
No, I just watched the video, but then we go to the book.
Yeah, no problem. But I mean, I'm sure you're probably familiar with this. Like, this is just saying, this is about the whirlpool galaxy we examined in the first section in this chapter. Galaxies are as immense as atoms are small, yet the same laws of physics describe both, along with all of the rest of nature, an indication of the underlying unity in the universe. The laws of physics are surprisingly few, implying an underlying simplicity to nature's apparent complexity. In this text, you learn about the laws of physics. Galaxies and atoms may seem far removed from your daily life, but as you begin to explore this broad-ranging subject, you may soon come to realize that physics plays a much larger role in your life than you first thought, no matter your life goals or career choice.
Oh, yeah.
So that's exactly what I was talking about. And then that's just talking about the scope of physics, calculate the order of magnitude of a quantity, compare measurable length, mass, and time scales quantitatively, and then describe the relationships among models, theories, and laws. So, there's some good things here about physics. Smartphones, looking at trains that levitate above tracks, invisibility cloaks, how the light is bending around them, microscopic robots that fight cancer cells in our body. All these groundbreaking advances, commonplace or unbelievable, rely on the principles of physics. So many professionals, many places, they use physics. Engineers, pilots, physicians, all that. There's ways that it's like looking at the X-ray, like X-ray machines. That's a physics principle, because you're using light and using the X-rays from that electromagnetic force. So So it's always good to get a good like introduction of understanding why, why we want to look at these units, and why we're looking at these units, what everything means. Right. So, and then say that again.
Do you know why we study these? And
Yeah,
how
for
we can
sure.
do it?
Exactly. Yeah, so and then the big thing is energy. Like, let's talk about the law of conservation of energy, which says that energy can change from form but is never lost. Ties together such topics such as food, calories, batteries, heat, light, and watch springs. Understanding this law makes it easier to learn about the various forms energy takes and how they relate to one another. Apparently unrelated topics are connected through broadly applicable physical laws, permitting an understanding beyond just the memorization of lists and facts. So I like that aspect. Science consists of theories and laws that are the general truths of nature, as well as the body of knowledge they encompass. Scientists are continuously trying to expand this body of knowledge and to perfect the expression of the laws that describe it. Physics, which comes from the Greek physis, meaning nature, is concerned with describing the interactions of energy, matter, space, and time. So that's exactly what we were talking about. Energy, forces, matter, what's in it, space, what's around it, and time, to uncover the fundamental mechanisms that underlie every phenomenon. This concern for describing the basic phenomena in nature essentially defines the scope of physics. So this one's talking about electricity,
Over here, the map.
GPS, Earth's landscapes, the exact distances between these. So, and then looking at speed, time dilation. Yeah,
We can
just
delay the time.
say it again.
We can delay the time.
Not delay, dilation. That's like the differences of time. It's like when a train's moving, and then I have one observer right here looking at it, and then as it's moving, I'm seeing it like that. But then for another observer, they're gonna be looking that way, this way. So that's kind of like a time dilation, because to one observer, this is shorter, and then for another observer, this is further. So that's pretty much time dilation. Like it looks like.
It depends on the position of where you actually.
Right. That has a lot to do with time dilation, like the changes. But then, for something like that, you might think, it's not that big of a deal. But what about when it's hundreds of thousands of miles away? That's when time dilation really comes to play, because there's some planets that have the retrograde motion. So, and then it might look like it's moving backwards, moves backwards, and then moves forward. Might look like it's moving backwards and forwards, but in reality, it might be doing something like there might be a certain star or something, or a planet or something right there, which is making it move in relation to that force. So, and then it's actually moving like in relation to another force, but but to us we can't tell. you know.
You mean the stars exert some forces that play a role when the planets move around?
Yeah, for sure. Like when it goes around each planet has, or each system, they say all the planets orbits, they say all orbits are elongated circles, not exact circles.
Oh,
So one of the things with that is that time is gonna move faster around here. So here's a star system. You know, typically a star might be in one place, but then there's also a counterbalance that happens if it's gonna be elongated. If it's gonna have an orbit that's not exactly circular, then there must be some counter force as well that's of equal magnitude over there. So this is important. I bring this up because you might think, oh, okay, it's gonna take this amount of time and it's moving the same. You might think that the speed should be the same. If it's 365 years, then or 365 days in a year, then it should move the same. We know it's gonna be 365, but that's not entirely true. There's a little bit of speed difference inside of our orbit with the sun, you know, much like we know about leap years and whatnot. So, you know, there's certain times where it's not exactly where it's not exactly 365. There may be like 0.12 days.
okay, so that's
you know.
why for example, when it's cold, we have 1 hour short, I think so. Like for the difference between the different countries. I know, for example,
Yeah.
for example, it's 4 hours the décalage. We have 4 hours like different. But for example, when it's cold, it's like 5 hours. It's gonna be like 5 hours, not 4 hours anymore. Maybe that's why they.
Yeah, so during the winter time, you're actually moving faster, and usually, like, I think y'all would be in the southern hemisphere, but if it's either way, it's either moving faster or slower. Like in our winter or even in y'all's winter, we're still gonna be going around the sun at the same time. So whenever it is, if it's winter time or summertime, you know, for us, we have longer days during the summertime.
Yeah.
But then you have shorter days during the winter time. So, and then some of this is because of this speed. You know, so the distance to get from here to here might be the same as that to that, but this is gonna be faster because you're getting more of this, like you're getting closer to this, I don't know, it's just the conservation of angular momentum, I guess. Like, because I'm getting closer to my counterbalance weight, my counterbalance force, then I'm gonna be moving faster along this portion. But then once I go here, I'm gonna start slowing down. So, and then I don't have as much force of this weight or that weight. So I'm kind of slowing down a little bit, and then I speed back up. So that's kind of like that time dilation too, because if I'm an observer, like I was talking about here, if I'm an observer looking at this, I'm like, wait, why is that going further? And then imagine an observer, you know, all the way over here, like our observation of time is gonna be dilated. It's gonna gonna be different. That's like,
even if you're looking at the same thing.
yeah. So, cause and then I'm already hundreds of miles away from where this person's looking, so they're already gonna be like way closer. But then if it's the other side, like the stars in Senegal are gonna look different than what I'm used to, most likely. Even though
so that's why, for example, the sun, for example, we see it here. For example, in Senegal before here, that's why we have this jet lag. The jet lag.
Yeah, jet lag is like time dilation.
Yeah. That's why.
Yeah, that's basically the same. Yeah, that's a good point. Yeah, that's a good point.
The sun is like here, and we have the world.
Yeah.
Moving around. That's why. That's what it is.
Yeah, for sure. Because we have different time zones.
Yeah, different times.
So and then as you're traveling from here, and then the sun rises in the east and sets in the west. So and then it might be a time. Like I might wake up at 7 a.m., but then as we're still moving too. So and then like as we're moving, it might, there's a 3-hour difference, or I don't know. We're like 7 something hours later than y'all. I think usually like 6 hours. I know Botswana's 6 hours difference. 4 hours difference. So yeah, that's a good example of time dilation. Yeah, that's a good example. Microwave ovens, blah blah blah, all that type of stuff. Microscopic and macroscopic. So I like that aspect. Rocks necessary to study all applications of physics formally. What's most useful is knowing the basic laws of physics and developing skills in the analytical methods for applying them. The study of physics also can improve your problem-solving skills. Furthermore, physics retains the most basic aspects of science, so it is used by all the sciences, and the study of physics makes other sciences easier to understand.
In chemistry, you will use it a lot.
Like it's forces, it's all forces. Like when
to understand how the electrons
right. At what time is the say that again?
The rate of
liters and like at what time is the combustion gonna happen? At what time is the boiling point gonna reach? It's all the same stuff. The scale of physics. So and then this is now about to start talking about the units, because we might look at certain things that are meters. Sheet of gold, tiny phytoplankton, where those are. So it says the individual atoms, like you were talking about, composed in this sheet of gold is A. B is phytoplankton near Antarctic Sea. They range from a few micrometers, which is 10 to the negative 6 meters, to as much as 2 millimeters, where 1 millimeter is 10 to the negative 3 meters in length. These two colliding galaxies, known as NGC 4676A and NGC 4676B, are nicknamed the mice because of the tail of gas emanating from each one. They are located 300 million light years from Earth in the constellation Coma Berenices. Eventually, these two galaxies will merge into one. So,
are we talking about in the microscopic level?
Yeah. So A is.
I can imagine.
Yeah.
It's in my mind, like it's too small.
Exactly. That's right. That's why chemistry was my hardest class, because it's so small. Yeah, it's hard to visualize.
It's okay. It's better here because where I'm from, they didn't have the material to show you that. Here you
Right.
have pictures, so like you can see at least you
Right.
have an understanding of what they're trying to say. But
Yeah, with more technology, we're able to see it better, and with the cooperation of YouTube, putting that together, and and then people are making good videos and putting things together. Like our microscopes are getting better, our telescopes are getting better. There's integrations of putting, like when we look at weather research, I'm able to use infrared data. So infrared would be good when you don't have as much light. There's sunlight, there's light and darkness. But what happens in the darkness? How can I tell the weather in the darkness? So I'm able to see each particle of each water droplet particle. So I can see each droplet. So that's why we have our infrared and radar infrared image weather images. Like all these. So that's where we get these from. Our infrared, be good for.
And you can tell from those images?
Yeah, so, of course, usually lighter colors are going to be less powerful, and then the darker colors, so typically light blue, green, and then orange, and then red. It's still that electromagnetic spectrum right there. Roy G. Biv, red. Red has a longer wavelength, lower spectrum. Blue has a higher wavelength. But in atmospheric physics, it would make sense that a longer wavelength would come up like this because it's a low pressure system. So it makes sense if it's low pressure. It makes sense that these would be a longer wavelength. The difference, yeah. See, like here, it's a much longer wavelength here. There's a larger amount of this low pressure system. This center is larger than the one that we were looking at here. So, and then the change in pressures is gonna be, this looks like a faster storm than this one. But this one's wider, so it may be a little bit slower moving, but it's a wider storm. So all that heat is going up and, staying there, and it's just like big thunderstorms, right around here. And then you're getting this wind, so it's pretty windy. It's gonna be windy. Conservation of angular momentum is gonna come into that point of low pressure. But then, like for this one, it's probably moving pretty fast. It looks like it's moving faster. It's got like a smaller low center, but it's obviously organized. It's organized system here. So anyway, that's like yeah. So anyway, that's like we'll look at, it's probably dark right here. It's probably not in the daytime, because if it was in the daytime, typically I'd be able to see this. So it could be the daytime, but we use it more when it's not the daytime, because like you say, we won't be able to see it as good. But you can see when that force is coming in. You can see how far this band comes, the low pressure. So those are some feats
and
of.
it's gonna tell you either it will rain or it's it's gonna be sunny, windy.
Yeah, so the rain. So as you see, so this is temperatures. So there may be some of them that are gonna look for temperature, and then some of them that's gonna look for precipitation. But because there may be different wavelengths that I can see the temperature as opposed to the precipitation or whatever. So, but even this, the way our world works, so you have a low pressure system, and then air is going to be moving counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. So a lot of y'all storms might move clockwise. But then in the northern hemisphere, our low pressure systems move anti-clockwise. So you'll see those bands that do like that, those cold systems. You'll see that because a cold air will be moving in from that way. If the air is coming in this way, cold air is moving in. So and then as this moves, I'm gonna be picking up on a horizontal level the air is gonna be coming in, and then it's gonna pick up. It's gonna shoot up the warmer air. So as this goes up and up, more and more,
that's why.
Then that's why you get these big thunderstorms. Because if it goes up real fast, the higher the greater the force magnitude of the force is going to go up higher and higher. So and then there's going to be condensation and the coalescence and condensation. So
I'm sorry. That's why when it's too hot, it ended up raining because we have too much.
Yeah, so it's humidity. So yeah, so and then there's constantly water. There's constantly water vapor in the atmosphere. There's constantly water, but then in desert areas, it still may be very, that's why it can get hotter and you don't feel it as much, because in the desert areas it's more dry, but it's like 130 Fahrenheit, whatever. It's 130, but yet, it's hot, but humidity is even worse, because humidity adds water vapor. That means that water vapor is present, so there's more water vapor. So and then our bodies can feel it more. Like it's muggy. Like I'm sure you could tell a difference these past few weeks.
Yeah.
Like it gets muggy, it's hot, and you're just sweating, and it gets real muggy. So so this has to do with it. Like it's as so we have our ocean. So we can have the ocean, and then over land it's gonna have a different heat capacity as over the ocean. So you're always gonna have these differences in